All right, let's talk about the biggest engine in our solar system, the sun. I mean, it's the ultimate source of pretty much everything. Our weather, our climate, you name it. So, how does this giant nuclear furnace, 150 million kilometers away, run the whole show here on Earth? Okay, let's dive into this. Seriously, think about that distance for a second. It's mind-boggling. And yet, the sun dictates everything, from a nice gentle breeze to a Category 5 hurricane. How on earth does its energy cross that cold, empty void of space to shape our entire world? Well, that is the big question we are going to unpack right now.
It all starts with this constant stream of energy, like a cosmic package sent special delivery from our star straight to our front door.
Now, the scientific term for this energy package is insolation. It's kind of a mashup of three words: incoming, solar radiation. See? Insolation. It's basically all the solar energy that reaches Earth, and it travels in the form of shortwave radiation. Think of it as the raw fuel that powers our planet's engine. And this energy moves fast. I mean, light speed fast. It blazes across that 150 million kilometers, and it takes just 8 minutes and 20 seconds to get from the surface of the sun to the top of our atmosphere. Incredible. So, how much energy are we really talking about here? Well, scientists needed a baseline, a way to measure the sun's raw, unfiltered power. And they measure it right at the very edge of our atmosphere, using something called the solar constant. And that number is a whopping 1,367 watts per square meter. Now, to put that into perspective, imagine more than 13 of those old-school 100-watt incandescent light bulbs, all shining on a little patch of ground just big enough for you to stand on. That is a colossal amount of energy hitting our planet every single second. But here's the thing. Not all of that energy actually makes it to the ground, and it's definitely not spread out evenly. Before it can warm us up, that energy has to run through what you could call Earth's great energy gauntlet. And here it is. This is the number one reason why the equator is hot and the poles are freezing cold. It's all about the angle of the sun's rays. In the tropics, near the equator, the sunlight hits us head-on, like a super focused, intense flashlight beam. But as you move towards the poles, that same beam of energy hits the Earth at a slant, spreading the energy out over a much wider area. It just gets way less powerful. We've all made this mistake, right? You wear a dark shirt on a scorching hot day, and you just feel like you're baking. Well, that simple experience is the perfect way to understand our next crucial factor. It's all about something called albedo, which is really just a fancy word for how reflective a surface is. Bright surfaces like snow and ice, they have a high albedo. They're like wearing a white shirt. They reflect a ton of that sunlight right back into space. That dark surfaces, like oceans or forests, have a low albedo. They're the black shirt, absorbing that energy and heating up. And of course, a few other things are at play here too. The length of the day, that's a big one. Longer summer days just mean more hours of sunlight, which means more energy gets absorbed. And the transparency of the atmosphere matters a lot. A thick layer of clouds or even a lot of dust can act like a giant shade, blocking and reflecting energy before it ever gets to us. Okay, so we've got all these things that decide how much energy gets through, which brings up a really big question. With all this energy constantly pouring in, why doesn't the Earth just get hotter and hotter until it boils over? Well, the answer is that our planet maintains this incredibly precise heat budget. You can think of it like a cosmic bank account. The core idea is simple, but it's also profound. For the planet's temperature to stay stable, the energy coming in has to equal the energy going out. Your deposits have to equal your withdrawals. It's a really, really delicate balance. Let's break this down. Imagine 100 units of solar energy show up at the top of our atmosphere. Okay, right off the bat, about 30 of those units get bounced right back into space by clouds and bright surfaces like ice. That's the planet's albedo at work. Another 20 or so units get absorbed directly by gases in the atmosphere itself. So that leaves just 50 units, only half the original amount, to actually be absorbed by the ground. And to keep that budget balanced, all 100 of those units have to eventually find their way back out to space.
But, and this is a huge but, this cosmic bank account is not balanced everywhere. The tropics, they actually take in way more energy than they radiate back out, which creates this massive heat surplus. Meanwhile, the poles lose more heat than they gain, creating a constant heat deficit. This global imbalance is the fundamental engine that drives all of our weather and all of our ocean currents.
So we know the ground absorbs most of the energy that gets through. But then how does the air around us, the air we're breathing right now, actually get warm? The answer is, well, it's probably not what you think.
Here's the critical point, the big reveal. Our atmosphere isn't really heated by the sun's rays passing through it from above. No, it's heated from the bottom up, by the Earth's surface itself. Okay, here's how it works. First, the ground soaks up the sun's powerful shortwave energy, and it gets hot. Then, it radiates that heat back out, but this time it's a gentler, long-wave heat energy. The ground basically becomes a giant planet-sized radiator.
The next step is conduction. This is super simple. Just like a hot stove heats up the pan sitting on it, the warm ground heats up the tiny, thin layer of air that's in direct physical contact with it.
And the final piece of the puzzle is convection. That thin layer of air is now warm, which means it's lighter and less dense than the cooler air above it. So what does it do? It rises. And as it rises, it carries that heat energy upward, mixing the atmosphere. This process is what creates thermal currents, and eventually it's what makes clouds and weather. So remember that whole global heat imbalance thing, that surplus at the equator and the deficit at the poles? Well, the planet is constantly trying to balance its books, and it uses two massive circulatory systems to do it: atmospheric winds and ocean currents. They act like a global conveyor belt, constantly picking up extra heat from the tropics and shipping it toward the cold, energy-starved poles, just endlessly trying to even things out. So with all this energy arriving, getting absorbed, being reflected, and getting moved all over the planet, how do we actually make sense of the temperature patterns that all this creates? Well, that's where mapping comes in. Scientists use a tool you've definitely seen on weather maps before. They're called isotherms. And the idea is really simple. An isotherm is just a line that connects all the places on a map that have the same average temperature. By drawing these lines, we can actually see these huge global temperature belts and visualize the real-world effects of everything we've been talking about. And one of the biggest patterns these isotherm maps show us is the massive difference between land and water. Land heats up and cools down super fast. This means that inland areas get what we call continentality. Think brutally hot summers and freezing cold winters. Coastal areas, on the other hand, have a maritime influence. The ocean acts like a giant thermostat, soaking up heat in the summer and releasing it in the winter, which leads to much, much milder seasons. So we've seen how this incredibly delicate balance of incoming and outgoing energy has created the world we live in, a world where life can thrive. But that balance, it's not a guarantee. And that leaves us with a really critical question. What happens when we start tinkering with the rules of this cosmic energy budget? What happens if we change the planet's albedo by melting ice, or if we change the atmosphere so it traps more of that outgoing heat? Well, that is the challenge of our time.